Hello, my name is Andrew Kucher, and today I'm going to be solving problem 9.011 or 9.11 from the Fundamentals of Heat and Mass Transfer book by Bergman and Levine. Uh, brief, this question has a pretty simple, posits a very simple question, which is given a suspended plate of dimensions 0.15 by 0.15 meters with 5 millimeters thickness, and a quiescent air around this hot plate at 75 degrees Celsius for the air, and the plate itself is at 15 degrees Celsius. Find the average heat transfer coefficient between the plate and the air, using similarity and empirical principles, or equations rather. Uh, some very brief assumptions before we even get into this. Uniform temperature is assumed across the entire plate and like basically everything. Quiescent air, basically the air is not moving, so it's static, it's just perfectly still. Radiation is completely ignored in this, it's negligible. Steady state steady state constant properties, nothing's changing with time. Perfect gas behavior such that beta equals 1 over TF. So start off with air properties. TF in this case is the temperature of the fluid, which is it's just the average of the air and the plate. So that's 318 Kelvin at 1 atmosphere. And then that gives us a uh, rho. I forget the exact name of that symbol, but that gives us the properties of alpha 25.2, Prandtl's number 0.705, uh, conductivity K of 0.02676, and a still forget the name of that symbol, but the V is 17.7 times 10 to the negative 6 meters per second squared. The alpha is also times 10 to the negative 6 meters per second squared. Um, Now we need to get the Rayleigh number first, as you can see here, to determine if it's laminar, and what equation we will be using if it is or isn't laminar. Uh, The Rayleigh number is given using this equation and just plugging in the numbers. The temperature difference in this case is from the plate minus the air minus the surface. So it's positive. And yeah, so that gives us a Rayleigh number of 1.4 times 10 to the 7, which is less than 10 to the 9. So it's laminar flow. Now, the similarity solution using section 9.4, the equation found in section 9.4, gives us a Nusselt number of, well, obviously HL times L over K, but in this case, that's equal to 4/3 GRL divided by 4, all raised to the 1/4, times G of the Prandtl number. G of the Prandtl number is this equation here, which is 0.75 Prandtl to basically square root of Prandtl number all over 0.609 plus 1.221 Prandtl, again, square root of the Prandtl number, plus 1.238 times Prandtl number. And that entire thing is raised to the 1 over the fourth. Plugging in the values for the Prandtl number from the air properties gives you a value of GPR of 0.5. And in this case, the capital GRL is the Rayleigh number divided by the Prandtl number. So this gives us for the similarity solution, or similarity method, a average heat transfer coefficient of 5.81 watts per meter squared Kelvin. Just plugging in the rest of the numbers, the GRL, the GPR, and then the K and the length of the plate. Now when you do it empirically, this gives you a lot more of a direct equation, which in this case is 0.68 plus, well, HL times L over K equals 0.68 plus 0.67 times the Rayleigh number raised to the 1/4, all over 1 plus 0.492 divided up by the Prandtl number. That term is specifically raised to the 9 over 16, and then that plus 1 is raised to the 4 over 9. And then you obviously multiply that by K over L. Plugging in the values and getting the solution, you end up with HL of 5.908 watts per meter Kelvin. I hope this is helpful. I'm just gonna leave the uh, pages up for like a split second just so you can get a good look at them. Yeah. For this one, it's specifically referencing a lot of the equations, especially for like referencing like Nusselt numbers. Those will change a lot depending on the specific, well, Rayleigh number, Prandtl number, stuff like that. The different constants and terms and requirements of the question, the parameters of the question that you're reviewing. So yeah, hope this was helpful. Have a nice day.